Hello and welcome to part 3 of this series of videos introducing the mathematics of signals. In this part we'll look at real-time harmonic signals. For a view of all of the parts in this series, please click the link at the top of the screen. So here's an outline. We're going to try and answer questions such as: what is a time harmonic signal? What are the properties that describe it? Why are they interesting and useful? And we'll write all these things mathematically as the basis for more advanced analysis that will come later. So what is a time harmonic signal? Well, the answer is that you've probably already seen one. We have quite a lot of television crews come to Salford making programs about audio and acoustics, and it's pretty common that if it's anything to do with audio, what producers will often want to see in the background is an oscilloscope showing a wave like this. And this on the screen here is a time harmonic wave. It's pretty much the first thing that anyone ever shows you if you're talking about audio. So you have already seen one. Let's just talk in a bit more detail about what it actually is and why it has these characteristics. So here we're on a slide. We've got a little graph here of the signal x of t versus time t, and there it is. So just like it was on the graph. And one of the things that we can see here, and one of the most important properties, is that it repeats versus time. It's what we would call a periodic signal. You can see it's the same pattern repeating twice here on this screen, but potentially as many times, potentially going on forever. And then the word harmonic basically means that it's got one tone or one frequency component in it. So we'll look a bit more about that in a minute. But in terms of the actual sort of properties that quantify it, the first one, that's the most obvious one, is the amplitude of the signal. And if you were to change this, it's going to scale the plot vertically. It's like turning the volume up and down, and the amplitude makes it louder. If it gets bigger, or if the amplitude gets smaller, it makes it quieter again, and it scales this waveform vertically. The second property is the period, or the frequency of these cycles, of this repetition. And changing the frequency scales the signal in time. So if you lower the frequency, you're going to get a longer period, a longer repeat period. That means it's going to sound lower. Or if you shorten it, so if you raise the frequency, you're going to get a shorter period, and it's going to sound higher in pitch. Mathematically, we're going to write this as x of t, our signal, is amplitude A, which has whatever units the signal had, times the cosine, that's the cosine from trigonometry, of 2 times pi times frequency, which is in a unit called hertz, which is equivalent to 1 over seconds, times time. And the frequency is the number of cycles per second, so it makes sense that it's per second, 1 over seconds. And you can write you can write sine instead of cos if you wish. Many people do. It makes very little difference to the analysis, as we'll see later on. And this is indeed the cos from trigonometry. It's to do with right-angled triangles, and it relates the length of the adjacent side of the triangle to the length of the hypotenuse at the top for some angle theta. Just one little thing here. Many of you may be more used to looking at angles in degrees, so you would have some sort of protractor like this, where your measurement in degrees goes from 0 on the right over to 180 over the other side, and then maybe continue to 360, or maybe you could look at going the other way into negative angles and back round to minus 180. Doesn't make much difference. But we will usually use radians, which is exactly the same thing, but written as a fraction of pi. So you've still got 0 in the same place. You go around to plus or minus pi at plus or minus 180 degrees. And then you get other angles, which again are sort of common angles in degrees that have fairly sort of compact forms that are worth remembering in radians, like pi over 2 is 90 degrees, pi over 6 is 30, pi over 4 is 45, etc., etc. So this is worth remembering because these will crop up in various places. But why is it that this triangle, these cosine waves, kind of turn up? What have they got to do with signals? So let's take that triangle. I'm just going to turn it around, put it vertically like this, and I'm going to say that the hypotenuse is going to be the length of the amplitude of the signal. That immediately makes this adjacent side a cos theta. Similarly, the bit at the top is a sine theta over there. And what we're going to do is we're going to say that theta is going to be equal to 2 times pi times frequency times time. So the contents of the little formula we had a minute ago. And what's going to happen because of this is that theta is going to increase with time at a rate determined by frequency. And what's going to happen is it's going to scribe out a circle. So it's going to look rather like this. And we could just give some axis labels on this so that we know that the vertical axis here is going to be actually our signal value, a cos 2 pi ft, because that, like, if you're thinking of the coordinate of the little dot at the top left hand corner of the triangle relative to the point where theta is measured, and similarly the horizontal axis for the coordinates of that point is a sine 2 pi ft, which has nothing really to do with our signal at the minute. We said we're going to use cos, but it's another term that's going to prove useful here. And yeah, so theta is going to be positioned around this cycle, around this circle, in the range 0 to 2 pi. When you get to 2 pi, you're going to get back to the top and start again. So this thing is naturally going to be periodic because it's just going round and round and round the same orbit. And it's going to be radius a, firstly because I said that the length of that hypotenuse was a, but also because cos squared theta plus sine squared theta is actually 1. That's a common trigonometric identity. Everything's been multiplied by a, so it follows that the radius is always a, regardless of theta. And it's going to complete a cycle f times per second, which means it's going to loop around faster when f is bigger. So let's have a look at what this looks like. Here we go. So we can see that as time is passing, theta's increasing, and this little dot is just going round and round and round and round. And it's going to go round and round forever, essentially. That's what the math says. Cos as a function, it just loops forever. It's periodic, and this thing's just going round and round, and that's all we'll see. Time keeps increasing, it just keeps doing that cycle. So let's have a look at what happens if we sort of trace the position of the vertical point, our signal versus time. So it's a bit like you were looking at this sideways and only seeing the vertical scale. And I'm going to plot that versus time. What will we see? Well, these two dots are going to move together, but I'm just going to trace the time history. So off they go. You can see they're moving at the same height along the screen, and that is, of course, tracing out our cosine wave we saw a minute ago. And that, in some ways, is a bit something nothing, but the important thing here is that you can really see that the circle diagram on the left-hand side is an orbit. It's a periodic cycle, and just looking at that from the side, so to speak, just looking at the vertical component, the cosine bit, without ignoring the horizontal bit, gives you one of these oscillatory time harmonic waves. And this has a period 1 over f. There we go. That's a repeat period. Now what happens if I halve f? Then things are obviously going to go slower, so we're going to go slower around the circle. That means that as time progresses at the same rate, we're going to see a slower oscillation. And that means that our period, 1 over the frequency, is going to double. It's going to get longer. What about if we double the frequency? Well, we're going to go around twice as fast. So there we go. Slightly more frenetic oscillations. And that means we're going to get a shorter period. F doubled, so the period halved. So coming back to our original slide from a few minutes ago, we can kind of say that these are the two first quantities that we're going to think of. Now we're going to put another little twist on it slightly here, and because writing 2 pi f all the time is a bit clunky, what we're going to do instead is define the term omega that equals 2 pi f. And this is called angular frequency because it's essentially how many radians per second you're doing to sort of go around that circle. It tells you the rotation rate, and and every time omega equals 2 pi or 4 pi or 6 pi or 8 pi, that's going to give you a full rotation around the circle. And that's going to give us the same frequency, so exactly the same, but it just is a slightly more compact way of writing it that we will use pretty much universally. So here we are with our more compact form. Now that's almost everything, but there's one other little thing in terms of these parameters, and that is what we call phase. It's an extra term you have on here as a constant inside the cosine bracket. And what does that do? Well, it shifts the signal in time. It shifts it horizontally. And phase being inside the cosine there has got units radians. In terms of what I said a minute ago, it doesn't matter which you use cos or sine to define these things. Actually, this is the reason why. Because if you shift cos by minus pi over 2, now I've actually shifted that wave up there by minus pi. Note that it's gone sort of backwards in time. That implies that phi is going to be negative. And actually I've moved by half a cycle in that animation, so I've moved by minus pi. If you move by a quarter, by just one of these divisions on the top graph, then we'd be back 90 degrees or back minus pi over 2. And then you would actually imagine that you saw a sine wave instead. So we have the identity that cos theta minus pi over 2 gives you sine. So you can actually just write time harmonic signals as cos or sine. You'll get exactly the same behavior. You just end up with a different value of phase for whatever physical behavior it is you're looking at. It should be 90 degrees or pi over 2 different. So that's why that makes a little difference. But what does phase mean physically? Well, one of the ways it can be understood is as a delay. So if I write a delay into this signal, and this is on the left hand side how I write that, I would say that t has had a bit subtracted off it, an amount tau, which is my delay. That's how I'd write this. So that's been sort of subtracted off before I've put it into the cosine bit. Then if I just expand those out, then I can kind of separate the omega t and the omega tau, and then I can define that phi equals minus omega tau. I can set phase to be whatever I like. So what I've done is I've just sort of turned the delay into a phase, and frequency crops up in there because you know how many cycles a signal does in a certain time within that delay period is going to be important, but essentially it's going to turn that delay into a phase, and quite often we'll see negative phases for this reason, because often we're dealing with delays, so the phase will often be negative, in which case we'll call it a phase lag. Now the other place you'd likely have seen phase is the phase reversal button on consoles, which is often mistakenly called the phase button, but it doesn't switch phase. Phase is a continuous quantity from like 0 to 360 degrees or 0 to 2 pi radians. What this does is it changes the polarity. And what you're doing there is essentially taking a phase and switching it by plus or minus pi or plus or minus 180 degrees. And what that does is it takes you halfway around the cycle, so that what you get out is negative of the signal. So that's why it's called, has a little phase kind of symbol on it, but what it's actually doing is phase reversal or polarity switching. To understand other phases, let's go back to our animations of these little crazy rotating fellas. And what I'm going to do now is I'm going to plot two things on here. I'm going to plot my original signal with no phase change, x, in black. I'm going to plot another signal y that's the same thing but with a little phase change on here in blue. So I've got my cosine signals, the signals I'm actually interested in, on the vertical axis. I've got the equivalent sine ones on the horizontal axis. And in this example I've chosen that the phase is going to be minus pi over 3, so minus 60 degrees. And you can see that theta in the left-hand diagram is rotating anti-clockwise, whereas this phi, this phase lag, has caused the blue line to move back by 60 degrees. I've written minus phi there just to indicate that plus phi would still be in the same direction as theta, and this is negative. So what happens when this thing rotates? Well, they're both going to rotate because theta is going to increase with time, but theta is omega t, remember. But they're going to have this offset, and the offset's going to stay the same. So let's see what happens. They're just going to spin round, but the blue one's always going to track behind the black one by this phase lag. And you can see that that's caused these two signals to be delayed in time. And if you looked at these just on the graph, it's not always obvious what exactly is happening. In particular, if you kind of looked at the instantaneous values, the two blue dots, they seem to just sort of be moving kind of out of sync with one another, and it's quite difficult to sort of see what's going on. But if you plot this on the circle, you can see that they have this kind of rigid kind of relationship where they're just a certain number of degrees apart, and that is causing the behavior where one is kind of chasing the other one. And that is probably the best definition of what phase is. You see these things, the diagram on the left in electrical engineering, they call them phasors. That language doesn't seem to get used in acoustics that much. So that's the three quantities to define what's going on with the signal. We've got amplitude, frequency, and phase. Now let's get back to our signal statistics, which we had from the first talk. If you can't find that, please go back to the first lecture and you can pull that one up. So we've got these three quantities, which, because these signals are continuous, I'd written often in terms of integrals. And we've got the mean value of the signal over some period, time period 0 to t. And we know that that's usually 0 for audio signals because they're usually relevant, so relative to some reference pressure in air, or they'll be sort of generally tend to be biased to 0 in audio devices. We've got the peak, the maximum amplitude, be it positive or negative. That's what the little lines around xt mean there, which tells you about whether the signal's likely to clip. And then we've got the root mean squared RMS amplitude, and this tells you the most about signal power, because signal power is related to the square of the signal. So we've got the square in there, we take the mean of that, and then we square root it afterwards. So let's think about what these might be. So peak is pretty straightforward. You can see the peaks of the signal, and they're the same, positive or negative. They're just at plus or minus A, plus or minus the amplitude. So the peak is easy, it's A. What about the mean? Well, what we can do here is we need to average over time. And actually, we only need to average over one cycle, because one cycle tells you all the information about the signal, because it keeps doing the same thing again and again and again. You just need to consider one cycle, that tells you everything. So we'll just go from 0 to t there. And we're looking, because this is an integral, at the area under the curve. Now this is relative to 0, so what you see is the area above is positive, the area is negative. You look at those, you can probably tell visually that this is going to go to 0. The stuff below the 0 axis is going to cancel out the stuff above. So actually the average of that lot is going to go to 0, as we expect for an audio signal. That leaves us with the RMS, which is a little bit more complicated because we've got this square operation in there. So what we did for this in lecture 1 is we squared the signal. So let's take this signal and we'll square it. As I said, this is it's kind of like power. It's proportional to amplitude squared. For a signal, it depends what impedance, what load the signal's driving into, how much power is being conveyed. But you find that it's always proportional to the signal amplitude squared. So it's power with that caveat. What might this look like? Well, it's going to go positive, all be positive because it's squared. So even the negative values will go to positive. So we see that we go from positive due to positive, then to 0 because of 0, then to positive again because of the negative bit, and then back to 0 and so forth. So it actually looks like a cosine wave of half the amplitude that's been pushed up by a little offset. And we're going to take the mean of this to get the RMS, so the root of the mean of the square. And again, we can just look at one period. I'm going to pick to look at one period of the original signal to give a fair comparison. That's the area under the curve. We can immediately see this is all positive, so we're going to get something non-zero now. But what is it? So that's what we're trying to evaluate here for the mean square, the area under that curve. And the first thing we'll do is drop in our definition for x. So we're squaring it, so it's a squared, then the cosine all squared. And there's an identity for cosine squared, which is half plus half of 2 times whatever was in the bracket. And that is what we'll see. Now, my original signal phi was 0, so that does nothing, but the frequency 2 omega t, that's getting doubled, so that explains, so the half explains why we're seeing this sort of vertical offset, and then this sine wave, this cosine wave on top, and then the 2 omega t explains why it's oscillating twice as fast as the original signal. And what does this evaluate at? Well, we can break these two terms up, so we'll substitute that into the integral and we'll just break the two terms up. So first of all, we've got a squared over 2t. I've taken the half out of the integral there. And with that, just leaves us an integral of 1, which is very easy. An integral of 1 is t. It's just the length of the integration region. So that's going to come out as a squared over 2. But what about the second bit, this integral of cos 2 omega t plus 2? So let's just do this visually again. So there's our a squared over 2 from the first term on the graph. So this second bit is the difference plus and minus that. And again, we can see that this keeps changing phase. It goes negative as much as it is positive. And if you integrate all that up, add it all up, you'll find that it gives you 0. So the final answer is that you can just forget about this complicated second bit, and it is literally just that first term, which makes life a lot easier. So that is our result. It is just that mean of this this sort of funny raised signal. Now the RMS squared to get from signal to power, we're going to square root to go back from power to signal, root of the mean of the squared, and that's going to then give you a over root 2, which is about 0.707a. And that is our result. So going back to the other slide, we can now report that the root mean squared is going to come out as a over root 2 squared, which is about 0.707a. So I've drawn that on there. And interestingly, all of these don't depend on the frequency and they don't depend on the phase. Finally, we have the crest factor, which is the ratio of the peak divided by the RMS, and we can divide these two. And what we get then is root 2, because the 1 over root 2 is on the denominator, root 2 comes up to the top, and the a's cancel. So we get root 2, which is about 1.41, and that is true regardless of the value of a. So it doesn't depend on any of the properties of the time harmonic signal at all. All it depends on is the fact that it's time harmonic. So if it has this kind of shape, it has a crest factor of 1.41. End of story. So that is the 3 properties of the signal, and that is their stats. Why are they interesting? Why are they useful? Better question. And the main reason, there's 2 reasons here. One is that you can use them as building blocks to create other signals. This is a form of what you might call additive synthesis. So some of you might have heard of this if you're into audio stuff. It's kind of putting signals together to make other more interesting sounds. And these pure tones, these time harmonic signals are probably the most basic building blocks going. But kind of in terms of our maths and our understanding of signals and our understanding of systems, it's interesting because it means that whatever processing or analysis works for time harmonic signals can be applied to other frequencies too. And you probably already do this if you work in audio. We often talk about the frequency response of a piece of equipment, e.g. a microphone or an EQ unit. The frequency response being the response when you put a frequency through it, when you put a time harmonic signal through it. But it's rare that we'll actually ever play one of these pure tone time harmonic signals through, because they're not very musical, they're not very interesting to listen to. Probably not going to do it very much. But the frequency response is useful because it also tells you what the device will do to other signals. And the reason that this works is because those other signals can be built up from time harmonic signals. They can be built up from frequencies. And we know this. I mean, you know, the human hearing system tells you this. We kind of know, and people have known for a long time, that, you know, sounds are made up of frequencies. You can kind of hear that tonality often to them. And certainly I found when I was learning about this as an undergraduate, I felt that audio interpretation really helped me understand this area, because otherwise you're just looking at maths kind of scratching your head. And I think actually the intuition that sounds is built out of frequencies is actually helps you with the maths here. So that's one reason. The other is that the way physical or electrical systems respond to them is much simpler than other types of sort of more general signal. So we can analyze the systems for the simple waves, get simple response, and then generalize that via the idea of a frequency response to other signals as well. So let's start off by looking at how time harmonic signals can be used as the building blocks of other signals. And the example I'm going to look at here is a sawtooth signal. Here it is. Many of you will have probably seen these before if you're interested in synthesizers. They're pretty ubiquitous there. You can see how it's named. It looks a bit like the teeth of a saw. And the mathematical equation for that is this here, where we've got 2 times the mod of little t time over big T, the repeat period, which is marked on the graph, minus 1. So I'll just introduce this mod operator because some of you might not have met that before. So that is defined as being the number in the bracket minus the rounded down number of the bracket, rounded down to the nearest integer. So t over t just goes up like the blue line here. So aside from the fact we divided big T out, it's just going to keep going up linearly. Whereas mod, as soon as you kind of get up to the next biggest integer, so up to 1, it's going to snap that back down to 0 again, because suddenly the rounded down number goes up an integer and that gets subtracted off, so it just keeps stuck in this range 0 to 1. For our actual signal xt, we've done 2 times that, and then we subtracted 1, so instead of going from 0 to 1, it goes from minus 1 to plus 1, has 0 mean. And it can be shown, we'll look at this next video, that this can be expressed as a sum of time harmonic signals. I've written this in terms of sine signals because it's a bit easier. And you'll see that as you go along in these terms, in this series, which keeps going forever, but I've just written the first 4 terms, you keep going up in frequency, 2 pi t over t, 4 pi t over t, 6 pi t over big T, etc. And they also keep getting smaller. We've got a 1 over pi in the first, a 1 over 2 pi in the second term, 1 over 3 pi in the third term, 1 over 4 pi in the fourth term, etc. So they follow this kind of regular pattern. We can write the whole series like this using this summation operator. So we use a little index n to indicate the individual terms. And I've also just introduced this notation omega subscript n just to write this a little bit more compactly. So this is the frequencies of these different frequency components. We will call them the harmonics of the sawtooth wave. So here's that word harmonic turning up again. So what we're going to do is we're just going to see how that works by just comparing the original signal to a version where we change the value of n. So we truncate that series to different points. So we only include a certain number of terms. And we see how accurate it is. So that's his x with a little tilde on top. That's going to appear in red in a minute, and you'll see that summation operator. What I've done is I've just made the upper limit finite at some value big N, and that's indicated on the right hand side of the graph. So we'll see when this plays in a minute how that changes. So we'll see the red line, which is the sum of the series, and then we'll see some little grey lines, which are all the individual terms that are contributing. So off we go. Skipped one then. So you can see getting closer and closer and closer to the sawtooth wave, the red line to the blue line, as you add more and more terms on there. Particularly in the middle of the wave where it's smooth, you're getting very, very good convergence there, matching very well. At the end, at the kind of discontinuity, you're going to get an increasing kind of wobble because you're trying to interpolate something that changes very, very suddenly, discontinuous, we would say mathematically, with some signals that are continuous that change smoothly. So you get this sort of wobble at the effect at each end. That's called Gibbs artifacts. Let's just play that again. The little grey terms that appear in there are the different waves contributing to this that get summed up. All these different terms in the summation, and you'll see that they get smaller as they get higher frequency due to the 1 over n. Okay, I played a bit more smoothly this time. So you can see that we can use these sine waves to represent other signals, albeit with some slight limitations. And then let's talk about the response of signal systems to time harmonic signals. And for many systems, when you input a time harmonic signal, of a certain frequency, what you get out is also a time harmonic signal of the same frequency. This is one of the most important concepts. So all that changes is not the frequency, all that changes is the amplitude and the phase. And because of that, because the system will react to all frequencies separately, it means you can analyze the response for each frequency independently because they don't interact. We can then put those responses together in a frequency response plot and understand how this whole system behaves to other signals. This is fundamentally the reason that frequency responses are useful. It's also the reason why time harmonic signals are so ubiquitous in acoustics and engineering. So the systems that we're looking at here, so they're directed in a simpler way. The systems we're looking at here are called linear time invariant systems. And many of the systems we're trying to design in acoustics are aiming towards being in this category. Some aren't, but it's generally what we're aiming for. Just to explain, it's easier to consider systems that aren't in this category. So a non-linear system could be a distorting loudspeaker. It adds some sort of fuzziness onto the sound, and that is extra frequencies that weren't in the original signal that it was producing. So it's added. You put in some frequencies and you got out others. A time varying system might be, for example, Doppler shift from a motorbike. So as it passes, you hear a change in pitch, you hear a change in the frequencies you are receiving, even though the sound, the frequencies it produced were unchanged. So the change in path length in the air propagation has caused the frequencies to be shifted because it's time varying. These systems won't be like that. There'll be things like loudspeakers behaving well, microphones, electronic circuits, rooms. They're all, roughly speaking, linear time invariant. So let's look at how a linear time invariant system might modify a signal. So one thing it could do is it could take an input signal and it could scale it by a gain G, some number G. So this could be a time harmonic signal as on the left, and then the output Y is going to be X times G. So if this is a time harmonic signal, then of course G will just multiply the amplitude A, nothing else much will change. And we can write that back in the form of the original signal just by saying, well, we're going to define a new amplitude A nu that explains this increase in gain. So we've still got the same form, just got a new amplitude. The system's just changed the amplitude. Or we could delay. We've seen this a bit before. So again, we put that time harmonic signal in, we delay by tau. So Y is going to be the input signal, X of t minus tau. That's how the delay is going to be applied mathematically. And if we just put that in, we substitute that in, we get this. We can break up the terms and we can incorporate the minus omega tau that's going to turn up into phi. So we're going to find a new phase that is the original phase minus omega tau. So the system has produced another time harmonic wave, but just with a slightly different phase. You've seen those two before. Now we get on to something a little bit different, differentiation with respect to time. Now, this is a mathematical operation. You might not think it has much to do with physics, but actually a lot of physical systems respond to time differentials of other quantities. So, for example, in an electrical circuit, an inductor will respond to the time differential of current. In a mechanical system, you might, for example, have forces to overcome acceleration, which is the time derivative of velocity. So these turn up quite a bit. And for a real signal, for an arbitrary signal like this, it's quite difficult to evaluate the differential. I talked about how to do this for digital system signals last time, and it wasn't too complicated, but they were all approximate. But for time harmonic signals, we can do it exactly, and we can do it really easily. And that is the form, if you know anything about how to differentiate a trigonometric function. If not, look it up. And that is what you will get. Sine goes to cos, and the omega that was multiplying the t came out. And again, we can convert this back to the sine form that we had originally by noting that cos was sine of something minus pi over 2. So we'll put that in, and we'll get the new amplitude and we'll get the new phase. So again, despite this being quite a complicated operation, differentiation with respect to time, all that's happened is the amplitude and the phase has changed. Finally, we've got integration with respect to time, which is the opposite operation to differentiation. And this might turn up, for example, with a capacitor in a circuit that stores current. And I've just written this integral here from 0 to t. So storing all the signal from time 0 to now. And if you evaluate this, you'll find that you get minus a over omega this time. So the omega's popped out, but it's a division. And again, we're going to cos, but we're going to minus cos. So that is what we've got. And again, we can just rearrange those things, turn the cos back into sine using the phase shift. And what I've done here as well is I've just used that cos is minus cos of an angle minus pi. So just sort of gone 180 degrees around the cycle to compensate for the minus there. So sort of put the minus into the phase change. And then we get a new amplitude, which is just a over omega, and we get a phase which is shifted by pi over 2 in the other direction. So again, change in amplitude, phase shift, despite being quite a complicated math operation. So these signals, you put time-harmonic signal in, you get time-harmonic signal out, even when they do quite complicated things. Finally, let's just look at what happens when you pass multiple frequencies for a linear time invariant system. So here's an input that's made of lots of frequencies. It's a bit like the Sawtooth we saw before. Pass that through an LTI system and we'll get an output that potentially looks quite different. It would be quite difficult to think how X might map to Y in a straightforward manner. It looks quite a different signal. They're quite different characteristics, probably sound quite different. But we can build X up from frequency components. Here they are. There are some different varying weights, similar to how we saw before. And the output can also be built up in terms of frequency components. And you can see here again that what's changed is comparing the two sides for each frequency is the amplitude and the phase. So this LTI system, whatever it might have been, for omega 1, it doesn't change the gain, but it changes the phase by pi over 4, same as some of the examples we saw before. For omega 2, maybe it's changed the gain by a quarter, maybe it's changed the phase by pi over 2. These are just numbers I've made up, obviously, just to indicate how a signal can get changed. Omega 3, let's say it doubles the amplitude of that frequency, changes the phase the other way by pi over 4. And finally, gain over half, changes it by a bit more, minus 3 pi over 4. So these things are all just sort of getting shifted about, and the net result is a signal that looks really quite different. The output signal looks really quite different to the input signal, but all that's happened to each of the frequency components is they've just had their gain and phase shifted, and we can understand and analyse that much, much more easily. So to wrap up, a time harmonic signal can be fully described by 3 properties. We have the frequency, which might be the number of cycles per second in hertz, or it could be the angular frequency omega in radians per second. We have the amplitude A, which will match the signal units, and we have the phase phi, which will be in radians. The basic signal statistics, the mean, the peak, and the RMS, only depend on amplitude A, and they do not vary with frequency or phase. So the mean is always 0, the peak is always A, the RMS is always A over root 2, which is about 0.707A, and the crest factor doesn't depend on any of them, it's just root 2 roughly equals 1.41 for all time harmonic signals. And they're interesting and useful because many linear time invariant systems react to them in a simple way. We find that they will change the phase and amplitude of a frequency component, but the frequency itself doesn't shift. So it's very easy to just explain how it changes. And each frequency component could be studied separately, and then you sort of put them all back together. And this is useful because more interesting signals can be built up from sums of time harmonic signals. And that's the end. So next time we'll formalise some of this by looking at building signals with Fourier series. Thank you.